carry on. So what is our next step? I mean, in a sense, we're just like doing always the same thing. We're trying to fulfill all our boundary conditions, all the considerations that we had up to now about the values of the wave vectors. They're also ingredients in solving our boundary conditions. And now we're going to actually, complete this, this derivation. Here, we're just looking at the spatial dependence on the surface of the boundary for all these things. And in order to have any hope of being able to solve our things, we needed these spatial dependencies to coincide with each other in the incident, reflected, and transmitted wave. We came to all these conclusions. But now we actually, can fix the coefficients, right? These vectors here in the boundary conditions. Okay, so let's just do that. Now there is one. Let's see. So let's just rehash, right? So I'm going back to what we had last time with the boundary conditions. So what we are solving are these boundary conditions that we wrote down last time. And now we assume at the interface between the two media that there is no free charge or free current. Okay, so I'm using the lower bit of the equations. So that means just, permittivity in 1 times electric field perpendicular to the surface in 1 has to be the same thing as in 2. The perpendicular magnetic fields have to be continuous. The parallel electric fields have to be continuous. And the parallel components of the magnetic field have to be related by the inverse permeabilities of these things. Okay, so these are the equations now that we will fulfill. Okay, so let's just see where we are. Okay, so here, just carrying on from where we were, I rewrote those 4 conditions here. Okay, so this is what we have to satisfy. Now, in our case, the perpendicular direction is the z-axis in this strange choice of coordinate system that I will ultimately blame on Griffiths. Okay, complete. Okay, so what this first condition means is that the z components of the electrical fields have to be related according to this ratio of the permittivities in 1 and 2. Okay, and of course, on the one side, I have the addition of the incident and the reflected fields, because those 2 things are present, like they're superimposed in space on top of each other. Okay, but they're just moving in different directions. The second condition, the continuity of the perpendicular component of the magnetic field, that's just, straight this one here, where, once again, these field things here, we had already fixed in terms of the electric bits, okay, that we had in the free wave solution that we were using here. Okay, so here, the B0 is just literally the 1 over V1 E0 incident, okay, etc. that you read from this. Okay, so I have this, and then continuity of the parallel components of the electrical field gives me 2 independent equations for the x and the y components of these fields, and then the same thing for the relationship between the parallel components of the magnetic field. Okay, so I've got a bunch of coefficients here to equate with each other. Now the problem is, or maybe the added richness of this problem as compared to the one with normal incidence onto the surface, is that there is now a physical difference between the behavior of a wave that has a polarization inside the plane of incidence or perpendicular to it. Okay, so once again, what did we do? We had a plane, we had a wave that came in at an arbitrary angle, reflected wave, transmitted waves. These 3 waves form a plane. Okay, we redrew our axis where I just take this whole construction and I just go, okay, so now there's no component to the waves in that direction. Everything happens in this plane. Okay, and this is the plane of incidence. Now you can see if I've got my incident wave, then it has a polarization but there is surely a difference between the electric field oscillating this way or this way. You see, there's going to be a different response. Okay, so we have to do these two calculations separately. Fortunately, once again, because of linearity, these are two independent waves. So I can just say that whatever wave you give me is a linear combination of a wave which has a polarization in the plane of incidence plus a wave that has a polarization perpendicular to the plane of incidence. Any wave can be decomposed like that. Okay, so now we can do the calculations for these two polarizations separately. Let's do the first one. We will assume that the electric field is in the plane of incidence. Okay, so once again, I have my incoming wave like this, and now it has an electrical field that does this. Okay, so it's got, you know, my coordinate system, I've got it like this. And then the reflected wave has also an electric field going like this. And the transmitted wave has an electric field going like this. Okay, like in the drawing. Now, our first condition, if I look at this equation here for the x component of the electric fields, left and right of the boundary, then this equation here gives me the following. So I just look now at the, I remind you, so the x-axis is now this one here. Sorry, actually, the one I'm going to use first is this one here. We're going to look at the z component here. Yeah, so and the z component was again, sorry, this one here. Okay, so what we had is that maybe we can even number the things. Yeah, so 1, 2, 3, 4, and 4, you know, 3x, 3y, 4x, 4y. So what we get from equation 1 is just that in the first medium, I'm now measuring the electric field along the z-axis. So on the left side, I've got some permittivity epsilon 1, and now the x component of the field is, you see, minus sine of theta I with E0 I. So I've got minus E0 I sine of theta I. And then I've got plus, so if this is theta R, we'll replace it for that. Then here I've got E0 reflected sine theta reflected. And this has to be equal to epsilon 2 times, here you see I've got minus sine of theta t. Epsilon 2 times, if I got space, maybe I'll write it here, is equal to epsilon 2 times minus E0t sine theta t. Okay, so that's the first condition. Yeah, and then 2 is a trivial condition in this case here, because so B is just perpendicular, right? It has no component in the Z direction. You see the B is coming in and out of the plane in each case here, so that's a trivial relation. So this is a trivial 0 plus 0 is equal to 0. The third equation, then I'm just looking at the x and the y. So for example, if I look at the x component, then that just tells me that E0I with cos theta incident plus E0 reflected cosine of theta r. That has to be equal to E0 transmitted cos theta t. Okay, and the once again, so the x and the y components, so the y component trivializes. There's only 3x giving us this non-trivial relationship here. Then the fourth relation, if I replace B0I by 1 over VE, like I had from the original three-wave equation, then the fourth equation here becomes 1 over mu1 V1 with the 2, so E0I minus E0R. This minus here comes from the conventions that we had for the axis. You remember that the B field is measured the other way for the reflected. Okay. And this has to be equal to 1 over mu2 V2 E0T. Okay, so these are all the equations that that we have. And it really is a question of, first of all, substituting the laws of reflection that we saw, namely that theta I is equal to theta R, and that N1 sine of incident angle is equal to N2 times sine of reflected, of transmitted angle. You can just replace that in there. So for example, here you see it, it kind of simplifies because theta I is equal to theta R. So then you get the difference here. Theta t, you get the ratio of the N1 over N2 also appearing here. You can then divide by sine of theta I throughout. Okay, and you get essentially a simplified equation. So let's just let's see what. So essentially, like a basic algebra. So for example, if I do that, right, I just do the isolation of these two things here, I get that E0 incident minus E0 reflected. That is a ratio mu1 over mu2 that we'll just call beta, or that we have called beta in the past, right? This is what we had in the so C normal incidence calculation. Yeah, so we had obtained that parameter also in there. You can also rewrite it as just the mu1 n2 over mu2 n1. Okay, so that's the first equation. It's the same as in the case of normal incidence. However, now the third equation here becomes different from what we had before. So 3, this one implies that if I take E0I plus E0R, then I've got some other factor here I'll call alpha E0T, where this this alpha, as you see from here, is just the ratio of the cosine of the transmitted angle with the cosine of the incident angle. Okay, this is a t, cos theta t over cos theta I. So that's it. We can now solve this system of equations here like we did before to express the reflected and the transmitted amplitudes in terms of the incident ones. So solving, what you get is that the E0 reflected is equal to alpha minus beta over alpha plus beta E0 incident, and you get that E0 transmitted is equal to 2 over alpha plus beta E0 incident. Okay, so these parameters here you can rewrite in different ways. So, for example, here we know that the sine of the transmitted angle with the sine of the incident angle is related to the ratio of the refraction indices for the two media. So here I could rewrite this as 1 minus sine squared of theta t divided by 1 minus sine squared of theta I with one great big square root on top of it. And this one here, I can then rewrite as 1 minus the ratio. Yeah, so it's just n1 over n2. It was now just, oh, all right. Yes. I don't know if you can still read my beautiful handwriting. Okay, so if I put back the incident angle at 0 in this equation, I just recover the equations that we had when we did the normal incidence calculation straight from the scratch. Okay, now I've just got these different coefficients here. Yes.
Missing like the sine or cosine equation 4.
Am I missing the sine or the cosine in that equation 4? So sorry, so this one is here. So equation 4. Equation 4, if you look carefully, it's actually exactly the same as the first one, because let's see, so the ratio of the sines of theta t and sine theta I is also equal to the ratio of the indices of refraction by Snell's law. And then these ratios here give you the same relationship. So equation 4 is the same as equation 1. And the one that is non-trivial that we just write here is the third equation here. Right? Yeah, so the only kind of important equations here really are equation 1 and equation 3, and the other two are either trivial or redundant. Yeah. Okay. So that's kind of the end of our calculation here. Okay, so these are now our reflection and transmission amplitudes given incident amplitudes for the special case of polarization, namely electric field, in the plane of incidence onto our surface. Okay, so here there's lots of fun physics to be done with that. So nota bene, if I take the incident angle to 0, we just recover the earlier results for normal incidence. Okay, so that's the first remark that you can have here. So that's one. Then if I take the incident angle to go towards pi over 2. Namely, what I'm doing is that I'm going more and more like this with my incident wave, and I've got an electric field that's like this. Okay, so it's kind of really grazing like this. Then when I take my theta I to pi over 2, then the sign of theta I is going to go towards 1. Namely, this parameter alpha here is going to blow up. So this alpha is going to go to infinity. And if alpha goes to infinity, then the reflected amplitude goes to the incident amplitude, and the transmitted amplitude goes to 0. Okay, so if you have grazing reflection of a wave polarized in the plane of incidence, there's total reflection coming in. And that's a very useful phenomenon, because you know, for example, that in optical optical fibers, the reason why optical fibers have any utility whatsoever is because of total internal reflection. Okay, so that's a simple consequence of, again, these things. Perhaps a kind of even more fun, the most fun bit. Yeah, so that's the most fun. The most fun is that there exists an angle that is known as theta B, Brewster's angle. I don't actually know anything about the personal life of Brewster. But anyway, so he found that angle one day at the pub and became famous. So at this angle, the reflected wave amplitude vanishes. Okay, so and this angle, so this theta Brewster, you can just work it out, because what you want to put is just alpha is equal to beta, but both alpha and beta are given in terms of functions of the parameters of both media. Yeah? So knowing the permittivity and the permeability of both media, you can calculate Brewster's angle. Okay, so you know, it's the arc sine of 1 minus beta squared divided by, yeah, so again, n1 over n2 squared minus beta squared. Okay, so these are just curiosities that have real physical consequences. So given two media like this, there is a very special angle where indeed the whole wave goes through. Nothing is reflected. It's identically 0. Okay, and things look different above and below Brewster's angle. Okay, so these are just like simple consequences of that. Yes, question. So essentially, complete total internal reflection can only occur at an angle which is bigger than Brewster's angle, like this. So it's so Brewster's angle is if you want the absolutely worst scenario for your reflected wave. So if you were like a fiber optics designer and you wanted to like sync your company as fast as possible, you would make sure that your wave was like coiled in such a way that when the waves bounce, they bounce at Brewster's angle, which means that no wave would come out of this. Maybe if you were trying to do like an attenuator of electromagnetic waves, then you would indeed just have boundaries at Brewster's angle for the thing, and then the thing would be attenuated as fast as could be. So I don't know if there's any industrial application of like screwing people's reflections like this, but yeah, I'm sure there are. Other question?
It says that the arc sign is to the power of 1/2. Is it?
So what I mean is that it's the arc sign of all this junk here to the power of 1/2. Yeah. Okay, but that's just like a little curiosity. So maybe just to complete here in the notes. So CF notes for this. You can have the reflection and transmission coefficients for this, and you know it's just obvious from what we've done this here. T is equal to alpha beta times 2 over alpha plus beta squared. Okay, so these are reflection and transmission coefficients. They add up to 1 as expected, because these are really related to energy flow at the boundary. And this is essentially all that there is to say about that. Yeah. Okay, so that's one calculation. Now, if we had much more available time, we could do the independent calculation now of the polarization perpendicular to the plane of incidence. And you see essentially what we're doing when we do that is that we just trade electric for magnetic field directions. Okay, so the equations look dangerously similar. And the conclusions look also dangerously similar, except for some treacherous minus signs that show up in the coefficients. But it's a nice exercise to try to work through them. I think the details are also in Griffith's books, if you want to tabulate it. But once you've done this calculation for the polarization perpendicular to the plane of incidence, you've got the absolutely general treatment of plane waves hitting an interface between two media. Okay, so that's cool. Are we good with this? Any questions?